Oxygen is the invisible force that animates our world, present in every breath we take. It's the fuel for life, powering every movement, thought and heartbeat in nearly every animal. Through respiration, oxygen unlocks the energy stored in food, making life possible. The efficiency of an animal's respiratory system sets limits on its size, speed, and complexity. In low-oxygen worlds, only small, simple creatures thrive. In oxygen-rich worlds, evolution can create giants. The concentration of oxygen in our atmosphere has changed dramatically over time, shaping the course of life. These fluctuations have driven evolution, opening and closing doors to new possibilities. By looking into Earth's past, we see how oxygen sculpted some of the most spectacular giants ever to exist. The story of life on Earth is, at its core, the story of oxygen. For billions of years, Earth's atmosphere had little free oxygen. The Great Oxidation Event changed that, but true abundance came in the Carboniferous period, about 359 million years ago. Vast, swampy forests of giant plants pulled carbon dioxide from the air and released huge amounts of oxygen. Dead plants didn't fully decompose, trapping carbon underground and letting oxygen levels soar. Oxygen may have reached up to 35%, far higher than today's 21%. The air was denser, richer, and primed for life to grow larger than ever before. Fires raged more easily, but for animals, breathing became effortless. Evolution seized the opportunity, and the world was set for a spectacle of gigantism. The Carboniferous was a time when the rules of life were rewritten by the air itself. This supercharged atmosphere allowed creatures to reach sizes unimaginable today. In the Carboniferous, arthropods, creatures like insects and millipedes, became giants. Dragonflies like Meganeura had wingspans as wide as hawks, hunting with power and precision. Arthropleura, a millipede relative, stretched over 2 meters long, dominating the forest floor. Scorpion-like predators grew to the size of house cats, ruling the undergrowth. These creatures' immense size was possible only because of the oxygen-rich air. More oxygen meant more energy, fueling bigger bodies and more complex systems. The giants of this era were living proof of how the environment shapes evolution. Why did high oxygen allow such giant insects? It comes down to how they breathe. Insects use a network of tiny tubes, trachea, to deliver oxygen directly to their cells. This system works well for small bodies, but diffusion limits how big they can get. In today's atmosphere, oxygen can't reach deep tissues in large insects. They'd suffocate. But in the Carboniferous, with 35% oxygen, the diffusion gradient was much steeper. Oxygen could travel further, supporting much larger bodies. The superoxygenated air overcame the physical limits of insect respiration. That's why Meganeura and Arthropleura could grow so massive. Their size was a direct result of the ancient atmosphere's chemistry. When the air changed, so did the rules of life. The age of giants ended as oxygen levels fell and the world's climate changed. Shrinking swamps and new microbes slowed oxygen production, dropping it to today's levels. Giant arthropods couldn't get enough oxygen, only smaller ones survived. Natural selection favored those who could breathe efficiently in thinner air. The story of these giants reveals how life and the planet's chemistry are intertwined. Today, our atmosphere limits insect size, a silent boundary set by oxygen. The rise and fall of these creatures remind us how fragile and interconnected Earth's systems are. The ghosts of the Carboniferous giants echo the ever-changing story of life on our planet.